Hello everyone, my name is Igor Kavric. Today I will present a topic on global ductility levels based on different local ductility levels of dissipative connections in cross-laminated timber buildings. Ductility in structures and capacity design should be ensured on different building levels, connection level, wall systems, and finally also on entire buildings. Determination of ductility of timber connections and assemblies is generally a pretty hard task as wood as material does not have as clear yielding point as materials such as steel. We follow the European EN 12512 standard, which is also referred and used in European building codes. Ductility is ratio between ultimate displacement and yield displacement and represents the ability of plastic deformations before failure. We based our study on a previously done experimental campaign on cyclic behavior of CLT connections and CLT wall systems. Typical connections in CLT buildings were systematically identified and each of them was tested in all directions. We extracted connection ductility values which were then used in numerical modeling. So we have experimental ductility values on hold down in tension, angle brackets in tension and shear, and screw connections in shear direction. Also, experimental ductility values on single or monolithic walls and coupled or segmented walls were compared. On average, more than 50% higher ductility values were reached in coupled walls compared to single walls. Then, we use these experimental values to calibrate and validate our numerical models. We made following assumptions in numerical modeling. CLT was modeled as linear elastic material. Hold downs were assumed to resist tension or uplift forces only, while angle brackets were assumed to resist both shear and tension forces with additionally applied shear uplift interaction domain. Trilinear approximation for connection response was used for nonlinear static or pushover analysis, and the models were verified comparing strand deformation curves in different parts of CLT walls. Experimental and numerical results matched well in terms of global backbone curves, left-hand side figure, uplift deformation in the wall's corners, presented in central figures, and sliding deformation on the bottom of the panels on the right side figures. We performed 3 cases on 4 different wall geometries with different aspect ratios and number of connections presented on the right-hand side figure. In case 1, we varied hold downs ductility while brackets ductility in both directions was constant. In this case, increased ductility of hold downs was effective only in narrow CLT walls, W1 and W2, due to predominant rocking kinematic mechanism compared to walls W3 and W4, where sliding kinematic mechanism is prevailing. In case 2, hold downs ductility was assumed to be constant, while the angle brackets ductility was ranging from 0.5 to 3 times the experimental value. Increased angle bracket ductility was effective in all wall geometry types as it increased global ductility in all cases. In addition, the deformation capacity increased linearly in all cases, as shown on the right-hand side graph. In case 3, we varied all local ductilities. In this case, we found linear correlation between local connection ductility, global wall ductility, and wall drift capacity. In addition to previously discussed outcomes, we observed that in cases where local connection ductility was higher than 1.8, wall types W1 and W2 satisfied the ductility class 3 requirements, also called high ductility class, while wall types W3 and W4 satisfied DC2, so-called medium ductility class, according to the current working draft of new Eurocode 8. There are, of course, still quite some aspects open for further study. Thank you for your attention and feel free to ask any question.